First is EC2 virtualization. We will start by clarifying some virtualization terminology. EC2 instances run as virtual machines on actual host computers in AWS, and these are located in what AWS calls availability zones. Each virtual machine will need an operating system, and there are many options available, including Amazon Linux or Microsoft Windows. Then, on top of the operating system sit your applications. Though each application runs on the operating system within a VM, some are designed to form an enterprise application across multiple VMs. Other applications form horizontally scalable services, made up of a few or many virtual machines working together. But there are still some applications that are designed to run on just a single server or virtual machine. The virtual machines themselves run on something called a hypervisor layer, which is maintained by AWS. The best way to describe the hypervisor is as the operating platform layer that provides the EC2 instances with access to the actual hardware they need to run, things like processors, memory, storage, and so on. Each EC2 instance will get a particular number of virtual CPUs, memory, and the like. Some EC2 instances use something called an instance store. An instance store is block-level storage, which means that the operating system driver can read and write to it at the block level, though application access usually happens at the file system level. This type of storage is referred to as ephemeral storage because it's physically attached to the underlying host computer in the AWS data center. Its content can only persist for the time that the EC2 instance runs on the same underlying physical host. If you reboot an instance, the data in the instance store will persist. But if you stop the instance, the data is lost because the underlying physical host will almost certainly have changed. Instead of an instance store, many EC2 instances use Amazon Elastic Block Storage, or Amazon EBS, for the boot disk and other storage. EBS gives us persistent block storage volumes so that the data remains even when the instance is in a stopped state. EBS-optimized instances are designed to minimize any I/O contention between EBS and other traffic from your instance, and this helps to provide better performance guarantees. EC2 instances will probably need network connectivity to a variety of other resources, such as other EC2 instances, object storage like Amazon S3 or Amazon Simple Storage Service, and the internet itself. The degree of network access is configurable to suit your needs and to balance accessibility with security requirements. Different instance types will give you different levels of network performance. Here's some more terminology. Instance types refer to the available selection of instances that you can choose for your workloads. There are many instance types. Some are general purpose, others are designed to give us extra CPU processing power, extra RAM or memory, or extra I/O network performance. There are many variations across categories, families, and types. One of the first things to consider in selecting an instance is the type of workload you want to run. Ideally, you want to choose the most cost-effective instance type that will support the requirements of the workload. Look at the instance type on the top right. This is a T3 Nano instance. It is part of the burstable general purpose category and a part of the T3 family of instances. And the Nano part refers to a specific instance type in that family. When you launch a T3 Nano instance, it comes with 2 vCPUs and 0.5 gigabytes of memory, and up to 5 gigabits per second of network performance, with its operating system on Amazon EBS storage. In contrast, the X1E32 Extra Large is a memory-optimized instance designed specifically for high-performance databases, in-memory databases, and other memory-intensive enterprise applications. It comes with 128 vCPUs, 3,904 gigabytes of RAM, 14,000 megabits per second of dedicated EBS bandwidth, and 25 gigabits of network performance, and a 3,840 gigabyte solid-state drive or SSD. You can find the details of all the instance types by searching for instance types in the AWS documentation. To find out more about how to choose the best instance for a particular use case while optimizing for cost, you can search for Cost Optimization EC2 right sizing, or compute optimizer in the AWS documentation. Now you'll get an overview of what it takes to provision an instance. You start with an Amazon Machine Image, or AMI. An AMI is the template that Amazon EC2 uses to launch an instance. Some AMIs are provided by AWS. Other AMIs are created by third-party organizations and are available in the AWS Marketplace. Another option is for you to create your own AMI from an existing EC2 instance. To launch an instance, you must specify a number of details in addition to telling it which AMI to use. The items you see here are not an exhaustive list of all the available options, but they do represent some of the most important items you must consider when you launch a secure instance. At launch time, you can specify network placement and addressing as appropriate to help secure the instance and provide access to it. All instances are deployed in a network, either the older EC2 Classic network or the current Virtual Private Cloud or VPC model. And you can also choose whether to assign a public IP address or DNS address to the instance. The storage type that the instance's operating system will boot from can be either ephemeral instant storage or an EBS volume. You can also retroactively attach additional block storage volumes to the instance itself later. You must also configure a new security group or use an existing one. The security group defines which ports network traffic is allowed on. You will also usually see a key pair associated with the instance at launch. This is mainly used for secure shell or SSH connections to your instance, or when you want to access it through Remote Desktop Protocol or RDP. Finally, you can specify user data when you launch an instance. This is a simple but powerful way to automate your installations and configuration on the virtual machines when it launches. You'll look at each of these options now in more detail. The first option is AMIs. An AMI provides the information that's needed to launch an instance, which is effectively a virtual server in the cloud. And you must specify a source AMI when you launch an instance. You can launch multiple instances from a single AMI if you need multiple instances that all have the same configuration. You can also use different AMIs to launch instances when you need instances with different configurations. And you can create a new AMI from an instance at any time. For example, you could launch 3 instances from the same AMI, modify each instance in a different way by changing their configurations or installing additional software on some of them, and then capture each instance as a new AMI. After you do that, you would have 3 new AMIs, and the changes you made to each instance would be captured as new templates for creating additional instances. All AMIs have a few things in common. First, an AMI includes a template for the root volume. That includes an operating system and perhaps also an application server or other applications and so on. And the AMI also includes launch permissions. These control which AWS accounts can use the AMI to launch instances, and they also enable you to make the AMI available to the public if you want. And then finally, the AMI also includes block device mappings, which refer to additional storage volumes, if any are included, to automatically attach to the instance when it's launched. In terms of selection, you can choose an AMI that is provided by AWS, an AMI that was built by someone in the user community, an AMI from the AWS Marketplace, or one of your own AMIs. When you launch an instance that will use EBS storage, there are a number of EBS volume types you can choose from. You can choose between a hard disk drive, or HDD, or a solid-state drive, or SSD. You have a couple of options in each of those 2 categories. Because most workloads have a combination of mixed random and sequential I/O patterns, SSD usually offers the highest performance compared to HDD. But HDD volumes are less expensive and have a dominant throughput characteristic, which usually maps well to workloads whose dominant characteristic is also mainly sequential access. Here's a summary of the options. First, provisioned IOPS, SSD, or IO1 volumes offer the overall highest EBS performance option. They're a good choice for I/O-intensive database and application workloads. They also work well for throughput-intensive database and data warehouse workloads, for example, HBase or Cassandra. Then, next under the SSD category are general-purpose SSD, or GP2 volumes. These are suitable for a broad range of transactional workloads. They work well for boot volumes and low-latency interactive applications. GP2 is the default EBS volume type for EC2 instances. If you need more IOPS than GP2 can provide, if you have a workload where low latency is critical, or if you need better performance consistency, we recommend that you use the previous IO1 option for provisioned IOPS instead. Also, to maximize the performance of GP2, it's important to use EBS optimized EC2 instances. Next is the first of the two HDD options, which is known as Throughput Optimized HDD or ST1. These volumes are backed by HDDs and are ideal for frequently accessed, throughput-intensive workloads that have large data sets and large I/O sizes. Examples include MapReduce, Apache Kafka, log processing, data warehousing, and extract, transform, load, or ETL. Again, like the previous example, it's important to use EBS-optimized EC2 instances to maximize the performance of this S21 storage type. The last of the four EBS options is known as Cold HDD or SC1. These offer the lowest cost per gigabyte of all the EBS volume types. SC1 volumes are ideal for less frequently accessed workloads with large cold data sets. Note that despite being the lowest performance tier, the burst model is still in operation here, similar to the ST1 option. When you launch an EC2 instance, you launch it into a VPC network environment. When you create a virtual private cloud, or VPC, you define a virtual network that is your own logically isolated area within the AWS cloud. You can then launch AWS resources, such as instances, into the VPC. It's often helpful to remember that a VPC closely resembles a traditional network that you might operate in your own data center. What goes into a VPC? In a VPC, you define one or more subnets, which are effectively logical network segments, each contained within a single availability zones. Subnets are often used as delimiters for which resources can access the internet. For accessing the internet, you must know about the Internet Gateway. Though it's simple to configure, an Internet Gateway is a fully horizontally scaled, redundant, and highly available component of a VPC that allows communication between the instances in the VPC and the internet. There are some topologies and workloads that do not need or should not have any internet access. If you must support a private connection to your own data center, a virtual private network, or VPN, is a commonly used option. You can use a component called a virtual private gateway, which sits on the Amazon side of the VPN. You create a virtual private gateway object and attach it to the VPC that you want to create the VPN connection from. The customer side of the VPN has a customer gateway, and it can be a physical device or a software application. The diagram shows one possible VPN solution, but there are many examples and topologies to choose from. Security groups are also shown in the network diagram. Each security group defines a set of firewall rules for your instances, which either allow or block inbound and outbound traffic. Security groups act at the instance level, not at the subnet level. So instances in the same subnet in your VPC could actually be assigned to different security groups. Be aware that if you don't specify a security group at launch, the instance is going to be automatically assigned to the default security group for the VPC. When you create a new EC2 instance in a VPC, including your default VPC, you must think about whether users outside of your private network should be able to access the instance. Here are a few things to keep in mind when you plan for that access. First, be aware that a private IP address is always assigned to each instance when it is launched, and it is allocated to the instance from the pool of private IP addresses that are available in the subnet. The private IP addresses allow communication between EC2 instances and the VPC. Though the private IPv4 address is mandatory, you have the option to assign a public IP address to an EC2 instance. This will be generated dynamically from a pool of AWS public IP addresses, and it can be used by clients to connect to the instance from the internet. If you stop an instance and then start it again, it's going to receive a new public IP address. But if you reboot an instance, it will keep the same public IP address. It's also important to be aware of elastic IP addresses. An elastic IP address is a publicly accessible IP address that's allocated from an AWS pool. It can be provisioned and assigned to an EC2 instance. It's similar to a normal AWS public IP address on an EC2 instance, except that an elastic IP address is static. You can also reassign an elastic IP address to another instance anytime you choose, which can be helpful for single server failover applications. A connection between two or more VPCs is known as a peering connection. Thanks for watching. See you in the next video.
Welcome to a demonstration of launching an EC2 instance. We're in the AWS Management Console. There are multiple ways to access the EC2 portion of the console. You could type in EC2 under the search function. I've been spending some time working on this demo, so it does appear in the recently visited services. And if I go to all services, look under compute, I see EC2. No matter which link I click, they all take me to the same place. In this case, we can now see the new EC2 console. Resources are highlighted here. We can see the different resources. We can drill down if needed. It's definitely an improvement. AWS releases new screens periodically. If I scroll down, I have the ability to launch an instance. The first thing I need to do is choose an Amazon machine image. This contains the software configuration, the operating system, perhaps the applications that are required to launch this instance. In this case, I'm just going to choose the Amazon Linux 2 AMI, but you can scroll through the 40 AMIs that are listed here to pick the one that meets your needs. In this case, I choose an instance type. This instance type allows me to go ahead and select the number of virtual CPUs, the amount of memory, the type of storage, and network performance that I need. In this case, I'm going to go ahead and leave it the default, which is the T2 Micro. I'm now going to go ahead and click Configure Instance Details rather than Review and Launch. I can configure the instance. This allows me to drill down and get very granular in terms of what I want to do with that instance. I can launch multiple numbers of instances. I can request spot instances. I can define network settings. There's a whole bunch of parameters here that I can go ahead and configure. I'm not going to change anything here, but I'm going to move on to the next screen, which is the Add Storage screen. Now, my root volume for this instance will be a general purpose SSD, a GP2. I do have the options here to change that, either provisioned IOPS SSD or IO1 or magnetic. I can also add a new volume here. By adding a new volume, I get 5 choices in terms of the type of hardware I want. I can adjust the size, I can encrypt it. There are a whole host of different things that I can do. Again, configuring this based upon my needs. I can add tags. In this case, I can go ahead. The purpose of a tag is being able to search and classify my inventory. So in this case, I can add a tag. In this case, we can say EC2 instance. And I can call it EC2 demo. I can also add another tag. Let's say we'll call this, give it name, and we'll say EC2 demo 1. I can also configure a security group. Now I can create a new security group. Again, the security group is a set of firewall rules that controls the traffic to my instance. In this case, I'm going to select an existing security group. Now, in my test account here, have also been playing with Elastic Beanstalk, so there are multiple security groups associated with my Elastic Beanstalk environment. I'm going to choose the default VPC security group and then review and launch. So I'm all set. I can go ahead and review as everything is configured, make edits and changes, and then I can go ahead and click launch. When I go to launch, it requests that I set up an existing key pair or create a new key pair. So this is the public key that AWS stores and the private key that I store to gain access to my instance. So in this case, I'm going to go ahead and create a new key pair. I'll give it a key pair name, EC2 demo 1. All right, again, after the name tag I gave it earlier, and I can go ahead and download that key pair. I can open it up or save the file. I'm going to go ahead and just save that file and launch the instances. So my instances are now launching. If I go ahead and click here, it has been initiated. You can see it pending. Now, some of the things that I have the ability to do is go up to the actions and click. And under instance settings, there are a bunch of different things that are going on. So I have the ability here to scroll down and get the system log. This will go ahead and show what's going on. So if for some reason I wasn't able to connect through SSH to this instance, I could observe boot messages through the terminal. In this case, I don't have anything happening right now as it's still initializing. And I also have the ability to go in and get an instance screenshot. So again, if there's some reason that I can't log in, I have the ability to go ahead and see here that what it would be on the login screen. So looks like that the kernel's loaded and is appropriate. So I'm going to go ahead and move back to instances. There's my EC2 instance. I'm going to go ahead and reboot it. And then I am going to go ahead and click the Get System Log. Now you can go ahead and see. Earlier, we weren't able to see anything because the boot process had already started and nothing was there. So I did want to make sure that you were able to see this. So again, another way to look at your instance and to see if there are any problems with it booting. In this case, there isn't. So again, that's a simple, quick way you can go ahead and launch an EC2 instance. Thank you very much and have a great day.
Welcome. In this module, you'll learn about security groups and also custom profiles for EC2 instances. Every instance must have at least one security group associated with it. Security groups are stateful firewalls that surround one or more EC2 instances, and they allow you to control the ICMP, TCP, and UDP-based network traffic that's allowed to pass through to the instance. It's important to understand that security groups are applied to specific instances instead of at the entry point to your network. And in addition to restricting which ports traffic can flow on, they can also be used to restrict which IP addresses that traffic is allowed to originate from. For example, if you set the source IP address range as 0.0.0.0/0 for IPv4 plus a :0 for IPv6, then traffic on that port will be allowed in from any source. However, you can also specify a particular IP address or a classless interdomain routing or CIDR range. You can also allow traffic to be sourced only from the AWS cloud, from instances that already have a specific security group assigned to them. This means the instances name other security groups as the allowable source to this one, which is like daisy chaining them or connecting them in a linear series. You can also assign multiple security groups to a single instance. For example, you can create an admin security group that allows traffic on TCP port 22 and a database server security group that allows traffic on TCP port 3306, and then assign both of these security groups to a particular instance. You can also apply a single security group to multiple different instances. In other words, security groups are very flexible. Security groups are either defined to work in the current Amazon VPC or the older EC2 Classic networking environments. For example, you cannot use an EC2 Classic security group with an instance that is running in a VPC. And be aware that EC2 classic security groups can only have rules that apply to inbound traffic, but VPC security groups can have rules that apply to both inbound and outbound traffic. Despite this, when you create a new VPC security group, all outbound traffic is open, and conveniently, you can add or modify your security group associations while the instance is running. We'll now talk about granting permissions to an EC2 instance, or more specifically, to the applications that run on the EC2 instance so they can reach each other's AWS services. When you want to grant specific access rights for AWS account services to applications that run on an EC2 instance or users who are connected to an EC2 instance, you can assign an instance profile to the instance. An instance profile is a container for an IAM role. An IAM role can have one or more IAM policies attached to it, and these policies grant temporary access to account resources. These access rights are granted by way of automatically rotated access keys, which are made available to applications that run on the EC2 instance through the instance metadata service, which you will learn about. Because this functionality exists, you can avoid storing permanent or semi-permanent access key and secret access key credentials on the EC2 instances themselves. Storing permanent access keys on EC2 instances is not a security best practice, and it should be avoided because credentials could become compromised. One example of where AWS account users can use an instance profile is when they want to grant EC2 instance permission to access the S3 buckets where application data is stored. To do this, you define an IAM role that is specifically demarcated for EC2 use and permits EC2 to use the role. The role itself should have an IAM policy attached to it that grants the necessary S3 permissions. You then assign this IAM role to the instance when the instance launches, or it can be assigned after the instance is launched. The instance profile container that contains the IAM role will be created automatically when you create an EC2 role through the console, though it's a separate action if you use the command line, and it must then be explicitly associated with the instance. One way you can customize an EC2 instance is by invoking user data when you launch the instance. User data is a powerful tool that can help you deploy EC2 instances in an automated and repeatable fashion. With user data, you can supply a script to a Linux or Windows instance. This script runs at instance launch as a series of commands during the end of the boot process. Scripts take the form of a shell script on Linux instances or batch or PowerShell scripts on Windows instances. Using user data, you can automate the setup of a new instance without needing to log in to the instance. Scripts do not have to do all the work. For example, a user data script could download and run a longer script that is stored in an Amazon S3 bucket. You can also download and install a configuration management system, such as Chef or Puppet, and kick off an initialization task from a reusable Chef cookbook or Puppet module. Also, you can call AWS CLI commands from your scripts. This process assumes you include code or instructions for installing the AWS CLI earlier in your script, if the instance does not already have the AWS CLI pre-installed on it. User data scripts are run by the Cloud Init service on Linux instances, or by the EC2 launch service on Windows instances. By default, user data scripts and Cloud Init directives run only during the first boot cycle when an instance is launched. However, you can configure user data scripts and Cloud Init directives to run every time the instance is restarted from a stop state. To learn how to run user data after the initial launch of an EC2 instance, search for User Data EC2 in the AWS documentation. User data on Linux can take two different forms. In the Linux shell script example on the left, the script starts with an invocation of a built-in Linux bash interpreter. You can invoke any interpreter that supports the Unix shebang or !! syntax and is installed on the base Linux AMI. For convenience, popular software language interpreters like Perl and Ruby typically come pre-installed on the recent Linux AMI images. In the cloud config example on the right, the directive is indicated in the first line and the rest follows the correct format to comply with what's expected by the Cloud Init service on Linux OS. When you use Cloud Config this way, it enables software to be installed when the instance is first booted, and it should be used whenever you must install software that will be available immediately after the instance boots.